Welcome everybody. Welcome at this next session of Getting Technical. The session of today is on micro vibrations in machining. My name is Patrick de Vos. I work since quite a long time for Seco, and I have a number of passions, professional passions. One is machining science, machining technology. And next to it, and that's perhaps my biggest passion of all, it's about knowledge around this machining process and skills and things, gaining it and sharing it. My biggest passion is to teach people in this very interesting thing we refer to as machining. Now, the basis for all the sessions we have in Getting Technical is what I refer to as the general machinability model we use. And machining as a process, and I prefer personally the term machining, because metal cutting can be confusing, because the moment people talk about cutting, they think on cutting cutting with a knife, where machining is cutting, but it's a different process. Machining is a process where I use a so-called cutting tool, and that tool I push through workpiece material. I deform the workpiece material by doing that, and I deform it so much it shears off under the form of a ship. That process is referred to as machining. And machining, understanding the process, that is what we aim for with what we call machinability and a machinability model. It's having insight in this process, insight to understand what's going on there. And basically you can see machining as a process where on the one hand you have a tool, a cutting tool with a certain load bearing capacity, and that tool is used in a manufacturing process that is putting loads on the tool, and we have to find a balance there, that the two things are in good combination, so things work as they are supposed to work. Now, loads acting on a cutting tool are coming from different sources. It can come from the process conditions, cutting data, the workpiece material, all that type of things are variables influencing the loads acting on a tool. And on the opposite side, there are the features of the cutting tool, the cutting materials, the coatings, the geometries, all that type of stuff, building blocks we use to create a cutting tool which is capable of handling the loads acting on the tool. And understanding the interaction is quite a vast domain, is quite a broad thing. And that is perhaps why sometimes people refer to as machining as a difficult. I don't think it's difficult. It's complex though. Yeah, quite a lot of variables. Because if you try to see the interaction here, you have to have some mechanical things to take into consideration. Tribological loads are acting on the tool. Thermal effects are taking place. There are chemical reactions. There is the environmental issue growing in importance more and more, and that makes that machining is quite a big thing. You know, there are so many variables in the equation, and that sometimes frightens people away a little bit, because I'm talking about people also, because as you can see in the schedule I'm showing on the screen here also, there is next to, how to say, the hardware things, the tool and stuff like that, there is also software, and software I refer then to knowledge and skills and insight, and that's what I refer to as the human effect in machining. So we work with machining, and after a while, of course, we ask the question, did we do a good job? Do we have a nice process? And for that, there are all kinds of things which are important. On the one hand, there is the knowledge and the skill sets of the people working with the process. And on the other hand, we need analytical tools to analyze the process. And that's what I show here in the picture. Perhaps the most powerful analytical tool to analyze a machining process is a global tool deterioration analysis. And on the other hand, the biggest impact on the machining process is I see is people and the knowledge of people. Today, as we talk about vibrations, we are going to concentrate on the mechanical side of machining. And the mechanical side, yeah, sorry, there were some vibrations in the process. The mechanical side, cutting forces. When we do machining, machining is a process where cutting forces are generated. I have to push the tool through the workpiece, and pushing, as the verb indicates, is forces. And cutting forces in machining, that's what I show with the diagram. They are rather high if you look into it, and those cutting forces have consequences. It's due to cutting forces that we need, amongst others, energy to do this process. That there are power requirements, that there are requirements on fixturing the cutting tool and the work holding, fixturing the workpiece, and cutting forces, when not kept under control, could lead to vibrations, which is the subject of today. Now, vibrations. First, very short, very briefly, what do we talk about when we talk about vibrations? A vibration is when a physical body moves to and from an equilibrium position, a position in rest. That's when we talk about an oscillation or a vibration. An oscillation is basically when the movement back and fro is rather low, while a vibration indicates that the movement is rather fast. A cutting tool on which there are no cutting forces acting when we don't use the cutting tool, or when the cutting forces are constant in size and in direction, or the tool will move from its rest position, from its equilibrium, or the tool will bend but stay stable, fixed. And that means no vibrations. Because if you don't have the to and from movement from the equilibrium position, you don't have a vibration. It's something we should be very much aware about. A cutting tool will only vibrate, or could start vibrating, when cutting forces are variable. Change in size or change in direction. Because then we will have a to and from movement, and a vibration could start. Now, that's very briefly some physical background. And if you look into this definition of a vibration, and if you take, for instance, an operation like a turning operation, in a turning operation you have a cutting tool. You do cutting. You have a certain depth of cut and a feed and a cutting speed. You have a certain cutting force. The cutting force will bend the tool, but will not lead to a vibration. Yet, we have vibrations in turning. So what are we missing here? That's the main subject of today. Why do I have, when I look on the one hand to the physical definition of a vibration, when we have a vibration, and on the other hand, I evaluate a turning application, why do I have vibration there? That's the main question here. And talking about vibrations, and I'm pretty sure you have heard lots of things and read a million texts and so 1 trillion videos on vibrations and all kinds of advice on vibration. But vibrations is very often, when we talk about it in machining, it's a finger pointing exercise. Because you have to see machining as something where you have a machine tool and you have a workpiece, and the workpiece is fixed on the machine tool, and you have a cutting tool, and the cutting tool is used with certain cutting conditions, and you have a cutting strategy. How do you move the tool over or in the workpiece? And all these things together form a dynamic system. And each element there can be the main reason, the source of vibrations. It can be the cutting tool, it can be the cutting conditions, but it could also be the machine tool, and it can be the workpiece. It can even be the operator, but when he was making wrong selections in cutting tools or cutting conditions, it could be that due to that the tool is used in the wrong way, the tool creates extra vibrations. And very often, I have been in a million discussions on this, and it's always finger pointing. You know, no, it's you, no, it's not me, and so on. One thing is for sure, that it's a rather complex thing, because I give here with 4 arrows in this example. Imagine you have one machine tool, you have one workpiece, quite a big one, you see the workpiece there, you have one application to do, whatever the application is, but the application can be done at 4 different places on or in the workpiece. Now, trust me, each of these 4 here will lead to a different situation. And in some of them, we will have vibrations, even if we use the same cutting tool on the same machine, in the same workpiece, and in others we don't have vibrations. So evaluating the vibration thing is not such a simple thing. On the other hand, it is like that the cutting tool and how it is used, the machining strategy and the cutting conditions, is in the equation here the most flexible variable, the easiest one to change. We could make an analysis here and say, okay, it's very obvious the workpiece is the cause of vibrations, but that's very nice, but the workpiece is the workpiece and I can't change the workpiece. The same could be with the machine tool. We could say, this machine tool causes the vibrations. Yeah, but the machine tool is the machine tool, and that's what we have, so we have to work with it. But the cutting tool and how it is used, that's the variable thing that we can change very easy. And that's why in most cases, we end up that people look at the cutting tool, look at the cutting conditions, and see what can we modify there to take care of vibrations. When we have to take care of vibrations, there are two approaches. When we are already at the level that we say, okay, we know the reason, but the reality is we will have to work with tooling, because that's the flexible thing. And then there are two directions to follow here. One could say, okay, I modify the cutting tool. The other way of working, personally, I prefer that one before changing the tool. That is evaluating cutting conditions and see if with an existing tool, but with another machining strategy, with a modified combination of cutting conditions, if I can't make the vibration disappear. Cutting forces, I already said in machining we have cutting forces. Cutting forces will bend a cutting tool, but will not necessarily make it vibrate. So we have to talk a little bit about cutting force variations. What you see here is a fast-moving video on how a ship is formed in case of steel machining. And what we see is that ship formation here is a rather fluent process. In comparison, for instance, to when I take the same cutting tool and when I start using or cutting in hard materials, what we see that the ship segmentation is of a completely different nature. And if you look a bit carefully, you see that the cutting tool, the relative movement of the cutting tool is like this kind of. It's doing this. That is called a vibration. That is called, more in particular, a microvibration. A microvibration is due to there are variations in cutting force during machining, and those variations can come, there are other sources, but this one is one of the major ones, can come due to ship segmentation phenomena. When you see the video on top, what you see is a fluid ship segmentation. The forming, the evacuation of the ships is going smoothly, and the cutting edge line, the cutting edge, is in a rather stable position, contrary to what that you see in the bottom, where ship segmentation is not so fluid. And the forming of the ship segments is an intermittent process. And this creates that the cutting edge line, that the cutting edge is having a relative variable movement on top of the normal movement. And that can create vibrations. We refer to it as micro vibrations. On the previous slide you saw was micro vibrations that started due to intermittent ship segmentation, due to hardness of workpiece materials. There are other things that could lead to intermittent ship segmentation. One of them is very typical what we find in machining of titanium alloys, superalloys. That is that in between ship segments there is a strain hardening effect taking place. The ship kind of wants to come loose from each other, but that process is kind of limited or interfered by that the material of the segment shows a strain hardening effect, and that leads to that like of a ship is working on a cutting edge line like a little hammer. It's doing like this, and there again you have your vibrations, and there again you have the situation that cutting forces are not constant, but cutting forces starts to vary. They go up and down. And that, as a matter of fact, is what is creating micro vibrations. So you kind of have the general cutting force, the stable cutting force, but on top of that stable cutting force, I try to represent here with the red line, there are potentially variations taking place. And those create a variable cutting force when they are added on top of the, let's call it average cutting force, the stable cutting force. Quite a lot of work here has been done by Professor Stahl at the University in Lund, already since quite a long time, where he was looking at what you see here on the graph is some of the pictures, where he was looking at a cutting edge line, a cutting point, let's say, and what you see in the little diagrams are different types of tooling, different combinations of cutting conditions, and every combination of cutting conditions and tool, in theory, and that is the red dot, would give the same cutting force. But if we look in reality, however, the cutting point, and that is the green thing you see on the diagrams here, the cutting point is making movements around the equilibrium position, the red dot here, and that creates micro vibrations. And you see here a movie, again high-speed movie, of a solid carbide milling cutter, because sometimes when we talk about vibrations, people say use solid carbide tools. They do not vibrate. Now, on a higher perspective, one could say no, indeed, they do not vibrate, as they do not bend, and when they do not bend, there is no risk. There is an oscillation going to take place. But from a micro vibration perspective, even solid carbide tools vibrate. And the proof of it you see here on the movie. It's a solid carbide milling cutter. It's an mill, and you see the movement of we talk about microns. Let's take the correct scale here. We talk about microns, but there is movement, so there are vibrations. It's what. Now, if we look at what you see here are diagrams of cutting force measurement. So this is reality. Let me explain a little bit. What you see in the table is left column, it's materials, different materials. What you see in the middle column is measured cutting forces. And what you see, and that's an interesting thing, in the right column is how a ship looks in this operation in section. And what we see in the case of steel machining, you see here two types of steel. Look first at the red line. The red line is the measured cutting force, and you see a rather flat line, stable, constant cutting force, one could say. If you look to the ship section, you see a rather fluently formed ship, what we refer to in daily terminology, a long ship. So traditional steel, no cutting force variations. The risk of having micro vibrations is rather low. On the contrary, when you see in the bottom a steel which is somewhat higher hardness, we see that higher hardness, the original flat line starts to variate a bit. And that variation we see is kind of indicating the risk for having vibrations is growing. This is cast iron. If you look to cast iron, if you look to the red line, the measured cutting forces, first of all, here you see all kinds of materials which are more or less comparable to each other from a mechanical properties perspective, the hardness, the tensile strength, that type of things, more or less. I hope there are not too many metallurgists in the group here listening to this, because otherwise I'm going to have a problem, I guess. But for the sake of the exercise, let's say we have here a comparable cast iron, and what we see here is that the red line becomes very doing this. Look at the ships in section. You see very heavily segmented ships, short ships, typical for cast iron. The risk here for vibrations, micro vibrations I'm talking about, is growing seriously. And a consequence, you all know if you machine cast iron compared to when you machine steel, that you find, relatively seen, more broken cutting edges. On the other hand, if you look to average cutting forces in cast iron are lower than in steel. Yet you have more broken cutting edges. Broken cutting edges indicate too high forces. And the forces are lower. It's not just the average you have to take into consideration. It's the variations you also have to take into consideration here. And that's the main issue here. Stainless steels. Look at the red line. I hope you start to feel the system behind this. You see different stainless steels here. Look at the red line, and you see again there's not a stable line. The line varies. Look at the segments of the ships, very irregularly shaped segments here. Risk for vibrations in this type of materials higher than in steel. Superalloys. Look at the ships, the section of the ships, the segmentation of the ships. Look at the measured cutting forces. High variations. And perhaps I should go, because here, if you look in the bottom, you see titanium. And you see an average cutting force of, let's say, around 1200 Newton. But you see a variation between, 1000 and 1400. That's 400 Newton over an average of 1200. That's 30%, people. I'm not talking about peanuts here. I talk about serious stuff. And these things, variations in cutting forces due to ship segmentation phenomena, that's the source of micro vibrations. And micro vibrations, you know, in most cases you don't even hear them, because people always talk about shatter and so on, and they say, listen, but micro vibrations, the frequency is so extremely high, you don't hear them. People don't hear them, but they kill cutting edges. Huh? And that's the whole thing here. That's why this insight is so important. Vibration tendency, micro vibrations, and workpiece materials. What you see here is just a little bit of a very big database, where we indicate based on types of materials and the hardness, because the ductility and the hardness to a big extent is a very good indicator for risk for having micro vibrations. Micro vibrations, be aware of that in steel, higher hardnesses create higher risks for micro vibrations. Be aware of that in case of cast iron, you will always have micro vibrations, and that's the reason why you have so many, relatively seen, so many broken cutting edges. Stainless steel, superalloys, titanium alloys, due to intership segment strain hardening phenomena, there will be micro vibrations. That's why in those type of materials, if you look to cutting edges, you have quite a lot of shipping due to this effect. And non-ferrous materials, we haven't been talking about those today, but perhaps one day we should spend some extra time, because those materials, they deserve the attention. They are so specifically. In non-ferrous materials, micro vibrations can appear due to build-up edge phenomena, which would lead to stick and slip phenomena during machining. What you see in the table here, what you see is just two examples: carbon steels and nickel alloys. In the carbon steels, you see ranges for hardness. And if you see the softer carbon steels with hardnesses below 125 Brinell, or let's say below 175 Brinell, relative vibration tendency, the risk for that there are micro vibrations appearing is basically 1, no risk. However, if you take a carbon steel with a hardness, let's say 400 Brinell, it's 2. You have twice as much risk that there are micro vibrations. And look at nickel alloys, typical Inconel type materials. There you see the risk for, or the relative vibration tendency, which is a metric for risks for micro vibrations, is 3.5. It's nearly 4 times as high. It's something we have to be aware of. If you say, yeah, but I don't have those tables, or I want to have more pragmatic approaches, but there are 2 things, like always in machining. Look at the ships and look at the used cutting edges. And if you have if you know what to look out for, that's for instance the technology we use in GTDA analysis, global tool deterioration stuff. If you see very heavily segmented ships, if you see without the obvious reasons that quite a lot of cutting edges show shipping to a rather big extent, it's 2 practical indicators that there is a risk that micro vibrations, in a very sneaky way, unheard, are killing your cutting edges, are killing the efficiency, the effectiveness, the reliability of your machining process. So watch out for those. And then, of course, people say, okay, perfect, I watch out. I observe, I see a risk. What do I do then? But also here to keep things a bit not too complicated. You have to, on a micro scale, you have to damp the movement, the relative movement of the cutting edge line around the equilibrium position, the actual cutting position at one point in time. And that is the mission here. Damp the tool. And there are a number of things we can do here. One thing that's perhaps a little bit already advanced approaches, that is working with synthetic flankware on cutting tools. It's kind of create a situation where cutting edge is forced into a constant contact with workpiece material, so there is no relative movement possible. This principle, in a somewhat modified way, is what we use when we talk about solid carbide milling cutters with a double clearance, a primary clearance and a secondary clearance. The primary clearance is basically the synthetic flankware principle we apply. It's no more or no less. You can also force a cutting tool in a damped position by selection of cutting conditions or by the selection of the machining strategy. I suppose you all heard about dynamic machining, and lots of people tell lots of things. It seems to be the big game changer in machining anyway, but dynamic machining, part of dynamic machining, or part of the advantages of it is that we force a tool into a fixed contact situation between workpiece and cutting tool. In doing so, we minimize variations on cutting forces. And in minimizing variations on cutting forces, we minimize the risk for micro vibrations. Now, it's easily said. I do know it's not always possible. But anyway, micro vibrations is something we have to watch out for because it's sneaky. You don't hear it, you don't see it, but you see the consequences. A questionable efficiency, effectiveness of a machining process, increased costs, unreliable behavior of cutting tools, all consequences of this micro vibration thing. And micro vibrations mainly refer or go back to how ship segmentation takes place. And ship segmentation is a subject in machining we have insight in, we know about. That's it. Are there questions? Ooh, I see quite a lot of questions. Let's the first question: if the temperature increase, more questions are coming anyway. If temperature increase, is there an effect on cutting forces and vice versa? In theory, if you would ask me to put my academic hat on, I would say yes. In practice, if you ask me to put my technologist's hat on, I say no. There are influences, but there are minor if you stay within what I refer to as a normal working window for cutting speeds. Is there any connection to the machine's resonance affecting micro vibrations? No, not really. It's two vibrations on top of each other. It could be in some cases that you start to have interference between things, but in a general thing, the two exist complementary to each other. Of course, if you have resonance vibrations already due to the machine tool, and on top of it you have micro vibrations due to the cutting tool, yeah, that's double negative. The third question, could we affirm that if we are obtaining segmented ship, we are having micro vibrations? The more a ship is segmented, the higher the risk is there are micro vibrations. Of course, there are things like the stronger the cutting tool, the more I force a cutting tool in having during cutting a fixed cutting line position, the less risk for vibrations. But in the general thing is segmented ships, the higher the segmentation, the higher the risk for micro vibrations. That's the general rule. And then together with that question is, could that be a symptom or a clue to look at? Yeah, of course. I always tell people, look at cutting edges, used cutting edges, look at ships. They tell you so much if you listen, if you watch. A segmented ship, it should for you say, double check on micro vibrations. And if nothing is going on, okay, perfect, but there is a risk. How does this theory interact with stability lobe diagram theory? Nothing. That's a completely different thing. That is the same thing as the question with the machine tool resonance. You have to see like this. A cutting edge moves. It has a movement vector. And normally, in theory, we suppose that that vector is constant in size and direction. A micro vibration is that a cutting edge on top of this movement does this. And that's a micro vibration. Or the term, the official name is ship segmentation vibration. I think that's a little bit, I call it micro vibrations. But stability lobes of machine tools, resonance stability things is a different thing. That has nothing to do with micro vibrations. How are micro vibrations correlated to chatter? That's a good one. Because what is chatter? If you should try Google what is chatter, you'll find a million definitions of chatter. I see it from a pragmatic perspective in such a way. Chatter for me is a phenomenon we can have during machining. And if that phenomenon gives me problems, broken tools, or more important, surface roughness quality problems of the machine surface, then we have to take it serious, because then it's jeopardizing the effectiveness, the efficiency of the operation. Seen like that, chatter, or seen like that, the relative movement of the tool around the normal movement will create extra surface irregularities, flows. So micro vibrations could take a form of how I define chatter. What kind of change in machining strategy would reduce micro vibrations? Any modification that leads to that the variation in cutting forces is lower, is smaller compared to the so-called average cutting force is good. Dynamic machining is good. It's good. Dynamic machining is a strategy that will minimize variations in cutting forces, at least in size, and that will lead to lower tendency for micro vibrations. Stronger geometries will increase the cutting force, the average cutting force will decrease variations. So stronger cutting edges, more negative acting cutting geometries minimize the risk for micro vibrations. it's about, you have to try to think. You take your strategy. You try to picture cutting force, average cutting forces, variations in cutting forces, variations in size and in dimensions, and it's not the size of the cutting force which is important. It's modification. Perhaps you know, this is a cutting tool. As a matter of fact, it's not a cutting tool, it's a pointer I use normally when I do live teaching. But let's call this a cutting tool. Let's say it's a milling cutter, and if I do this, cutting force, it bends. But do you see it vibrating? No. And if you push harder, it bends more, but it's still not vibrating. It's only when you start to do this, modified cutting forces, variations in cutting forces, this thing starts to vibrate. And you don't need to bend so much for that. It's the variation that makes the difference. Not the size, not necessary wise, only the size, the average cutting force. Wait, I have to keep track of the time a little bit also. During microvibrations, it is observed that the cutting edge elasticity deflects, or is it the tool hold? Ooh, that's a difficult one. In theory, both will deflect. For me, it's difficult to answer this question. Let me say, if you select a cutting material with a rather high hardness, it will be more the holder that deflects than the actual cutting edge line. The more you go towards softer cutting materials, the more it will also be the cutting edge line that starts to move. It's depending on the tooling you use. Would you recommend oscillation cutting on yeah. Yeah, you have a clever one. Because if you think on everything I said, short ships, segmented ships are not good. They could lead to micro vibrations. If you don't want micro vibrations, think opposite, create a long ship. A long ship in whatever material shows a 10, with the exception of cast irons, perhaps. I have to be careful a little bit here. But in most other materials, longer ships are more fluently formed. How do you create a longer ship? By reducing the feet. And in doing so, you see that you will have less micro vibrations, less segmentation, less shipping on cutting edges, longer tool life, and so on. But lower feeds jeopardize the productivity of the operation, the efficiency of the operation, or effectiveness, sorry. And here we have a dilemma. However, if you use oscillation cutting to break ships, that helps me, and I can find a new balance now with long ships on the cutting edge itself, but I break them with other means so they don't become a problem later on with evacuation and things like that. Oscillation cutting is an interesting method to evaluate in this situation. And yeah, I see the time is up, but questions continue to come in. Just one more, and then we have to close this. One question is, what is GTDA? GTDA, I mentioned it on the third or the fourth slide here. GTDA is an abbreviation. It stands for Global Tool Deterioration Analysis. It's an analytical tool which is developed to, in a structured way, because I think I said several times now during this presentation, look at your ships. look at your used cutting tools. They tell you things. But if you can do it in a more structured approach, not just have a look, but have a good look, it can give you a whole lot of advice on how to improve overall the different elements in the machining to, in the end, have a more productive, cost-efficient, reliable machining operation. And I propose we stop here because the time is up, and I'm pretty sure there are quite some more questions. Put them in comments. I'll try to answer as much as possible in comments. Be aware of, if you want to learn more about these things, that we have the technical education programs we offer to the machining industry, where we talk about machining from a scientific perspective or from a technological perspective, a little bit depending on the different courses we have. And I hope to see you during the next session, because already the next session is planned, where we talked a bit about ships now, but I want to talk a little bit more about ships on a more bigger scale, because ships is something which is from a practical perspective something we have to keep our eyes on, because if ships are not well formed, we can have micro vibrations, the subject of today. But when ships are not well formed, they could lead to other problems in the workshop. Or too long ships will stop the machine, because the ships needs to be evacuated manually. But the moment you have to stop a machine, that means the efficiency of the machine goes down. So ships is truly an important subject. Thank you very much for attending this. I hope in a short time, in a structured way, could enlighten you on a very complex subject in machining. I try to keep it pragmatic, so you can do something with it. Watch your ships, highly segmented ships. Watch your cutting edges, high level of shipping on cutting edges. Two indicators you could have micro vibrations. And micro vibrations, you don't hear them, you don't see them, but they are problematic. If you think there are micro vibrations, think in terms of cutting forces, variations on cutting forces, and think on your machining process, your machining strategy, your tool selection, your cutting condition selection. What could I do to minimize variations, to make cutting forces more stable, more constant in time? Thank you very much.